Welcome. In this video I'll discuss generalized Ohm's law, which is an extension to ideal MHD, which is often called the two-fluid model or extended MHD depending on which terms are kept. And it's basically allows a whole load of other waves to appear in the system and modifies the behavior, so things like the frozen-in theorem for ideal MHD becomes broken, and this leads to a whole load of interesting phenomena which are important in tokamaks and also more widely in plasma physics. So we'll start with the electron momentum equation, derived previously from the Boltzmann equation, and then show how this can be rewritten in the form of an Ohm's law, and then discuss the different terms in that equation and when they become important. So we can write down the momentum equation for the electrons. So here on the left we have the change in momentum, so d by dt of the electron momentum, so the electron mass here. On the right here we have the charge minus E, and then this is the Lorentz force on the electrons. We have the electron pressure tensor, so this is a tensor including the scalar pressure and also the stress tensor. And then this is the friction with other species, so this is basically becomes the resistance of the plasma. So this is collisions between electrons and ions. So what we can do is take this equation for the electrons and we can rewrite it in terms of the ion velocities. So the VE here is the electron velocity, so here we have VEs, these are all electron velocities. And what we're going to turn it into is turn this into ion velocities. So we're going to just write that we have here, so we have the J, the current, is the charge times the mass times VI, so the ions minus the electrons, and we write that the fluid flow U is roughly the ion velocity. So this is the because this is weighted by the mass of the species, and so because the ions are much more massive than the electrons, the flow of the fluid in MHD, for example, is the same as the flow of the ions. And so we can just write, and this V cross B, so E cross B velocity, for example, becomes, so then we can rearrange this equation here. You see you have here E plus here we're going to turn this into a U cross B, the fluid flow, and so this part here will become the ideal MHD Ohm's law, and then we just divide through by this minus En, and we rearrange this equation to put this ideal MHD part on the left hand side. And we can write down where here we have this term, this J cross B has combined with this U cross B to form VE cross B. So it's just coming from this substitution here, just turning V cross B into a U cross B minus J cross B. Here we have the resistivity terms. This just becomes the resistivity times J. This is the resistance term. Here we have an electron pressure term, and here we have an electron inertia term. So we have an electron mass here. Now these two terms here, the J cross B and the grad P, are the Hall terms. This is often called the Hall term, but this is at the same kind of order of magnitude. This is the electron inertia term and is often very small. So the Hall term is kind of analogous to what's called the Hall effect in semiconductors or other situations where you have for example, a magnetic field into the page, for example. You then run a current through a material, J, and due to the deflection of the electrons, what's seen is that you have an electric field forming across this way. So you have an electric field which is forming perpendicular to the current. This is what's happening here. So you have a current across the magnetic field gives you an electric field. And this is the Hall effect. So each of the terms on this right hand side here becomes important at different scales. So there's the resistance, so resistive MHD we've come across already, looking at things like tearing modes. Then the Hall effect terms are often important for some kind of waves and for reconnection. Then on the smallest scales the electron inertia becomes important. And so we'll go through these one at a time. So first the resistivity term. So as you've seen before, this term basically leads to diffusion of magnetic fields. So we have the induction equation and then we have dB by dt, that's curl of E. And if we substitute this term in here, if we neglect all of the terms, just keep the electric field is just equal to this this current times the resistance times the current density. Well, then you get, that's where we have, of course, that J is just 1 over mu naught curl of B. So neglecting any kind of displacement currents here. So we have J is curl of B, and if we neglect this bit, then this gives so if U is roughly 0, and if eta, so the resistivity is roughly constant. So then we get a diffusion equation, so we have dB by dt, and we have a diffusion coefficient times a second derivative of B. Let's create a vector. And so this is a diffusion of the magnetic field. And it becomes important when you can work out when it becomes important by balancing this resistive term against this term here, which we know is important in ideal MHD. And you see when does this term that we neglect in ideal MHD, when does that become comparable to this? So now we're going to try some dimensional analysis, so just taking these gradients as being equilibrium kind of length scales, or the length scales we're looking at, sorry. So we're going to just say that the gradients are roughly 1 over L, where L is a typical length scale that we're interested in. And then we can just rewrite this just in terms of magnitudes rather than vectors. So then we get a B on both sides, we just cancel those. One of the L's here cancels. And we just end up that this term is important when so in this term here we have mu naught L, U is here a typical velocity, L is a typical length, and here the resistivity, and this is important when this is roughly 1. So if it's smaller than 1, so if resistivity is high enough and this is smaller than 1, then resistance dominates, and if it's larger than 1, then the induction term, the U cross B term, is bigger. So if this term is much bigger than 1, then we have ideal MHD, this resistivity can be neglected. If this is 1 or smaller, then resistance is important. And this term, this quantity here, is the magnetic Reynolds number. It's analogous to the Reynolds number in fluid flow, except now the dissipation is the diffusion. Here there's eta of mu naught compared to the advection, the induction of the velocity and the lengths. If you choose the velocity to be typical, the typical velocity to the alphane, so the alphane speed, then this gives you that you have mu naught v alphane times the length scale over eta. This is called S, is the Lundquist number. And typically this is very large in fusion plasmas. So in the core and edge, this might be sort of 10 to the 6, 10 to the 7, that kind of area. There are regions of the plasma where this can become small, but its typical means that the resistivity and so magnetic reconnection is just important on small scales. And so typically what happens is you have small regions where the resistivity is important, and the plasma is not frozen into the fluid anymore, and so it can diffuse. A classic example of this is where you have let's say two kind of reconnecting plasma surfaces. So you have a set of flux surfaces like this, so magnetic fields here. So this could be due to a plasma at the top here, and this is coming in contact with another plasma underneath, and here we have currents going in the same direction. So we have currents, say, so the current going out of the page here and out of the page here. So we have a circular plasma field here, and this meets another field down here. This is just the B fields. Now in the middle here, what we end up with is a sharp change in the direction of the field, and so we end up with a current sheet. So here we have a thin layer of current where the magnetic field is changing sign. And so what happens here is that the field diffuses in to this layer. So it's diffusing in here, and then it's moving out this way. You have a reconnection region where the field is diffusing, so it's diffusing inwards. Well, it's moving inwards here, then diffusing across this thin layer, and then it's converted into flux is converted into heat, and you end up with magnetic fields like this. So in most of this region, it's essentially ideal MHD. So the plasma is moving inwards here, and it's moving out at the ends. In a very narrow region across this layer, if across this layer S, the longest number is about 1, and just across this very thin layer. And because this is dependent on the length scales, this layer is roughly 1,000,000 times smaller than the size of the system. So you have this very thin layer where ideal MHD is broken. Okay, so now we can move on to the next terms in the equations. So we go back to the form up here. So we looked at this resistance term and how that can break the frozen in. Next we'll try and look at this whole term here. So these two terms, so J cross B and the electron pressure term. So you can see when this is important by writing that, so J cross B over En, this is this whole term, and when that is roughly like the induction term, so U cross B, then this term is important, and so we can write this using this expression that J is 1 over mu naught curl of B, and again just do the dimensional analysis that the gradients are roughly like 1 over length. And so we can just write down that we have B squared, so we have a B from inside here and a B from there. We have a 1 over length. Then we have an E times an N and a mu naught from here. And on the right side we have the typical velocity U and again another B. And on these B's can cancel. Now we can write this in terms of some quantities here. So we have iron skin depth or inertial depth, and this is the square root. So using this quantity and this is a length and the alphane speed, we can rewrite this expression here. I can just write that delta I over L is roughly equal to U over V alphane. And so if L is small, comparable to this skin depth, then whole term becomes important. And so here delta I is the iron skin depth or inertial depth, or inertial length. And so on the small length scales where L length scales become comparable to this delta I, then a whole term is important. Well, I note that this depends on this ratio of typical velocities to the alphane speed, and so if the plasma is in fact not moving close to the alphane speed, so if typical velocities are smaller than this, then actually this term can become important at larger scales as well. So if your typical velocities are very small, then L can actually be quite large, and whole terms can still be important. Now the typical scale lengths, so we have this iron inertial length in a tokamak is roughly about 2 centimeters. If N is about 10 to the 20 per cubic meter. So you see that this is actually reasonably large for or at least non-negligible in a tokamak. The other term is the electron pressure term, and so this you can see very quickly what size this term has, because we must have in force balance we have that grad P is roughly J cross B, and the ion and electron pressures are roughly equal. And so this electron gradient of the electron pressure must have a similar order of magnitude to the j cross b term we just looked at, and so therefore this term has essentially the same scaling as the j cross b term. So if one of these is kept, the other one should be too, because they're both, just from force balance, they're both at the same order. And then finally, we can look at the electron inertial term, so the finite electron mass term. So we can just take one of these terms here. So just go back to have a look at this. This is quite a complicated expression, but if this is important, then essentially these terms here will be comparable. So you'll have sort of advection terms and time derivative terms. So if we can essentially concentrate on just one of these terms and say that if this is important, then this term here should be comparable to this term here. So here we just have an electron mass over En. There's divergence of U times J, and that should be comparable to this term here. And so again, the same thing applies. So here we have a J becomes one of mu naught L with the B, and so we can just write this whole thing as, so the B of mu naught L comes from the J, and we have another one of L from this gradient. On this side we have a UB, which cancels with this UB here, and so this we have an L squared, and then this term here. So all of this stuff here combined with this bit here, this is just the electron inertial length. So it's just delta E squared, where this is the electron inertial length. And so this is important when we have that the electron inertial length squared over the length squared is roughly 1. And so if this length is small or smaller than delta E, then this term becomes important. And delta E in a tokamak for the same density, so 10 to the 20 per cubic meter, is about half a millimeter. So you see that this only becomes important at very small scales. This is typically around or less than the ion gyroradius. So it can be important, but only at extremely small scales, much less than the whole term, for example. Okay, so that's a summary of the main terms. So you can see that these are the generalized Ohm's law terms, and ideal MHD is just this part. This is the ideal MHD part that we've been looking at so far. And we've now gone through the other terms which appear in a more complete models and seen when they become important. And so you have resistance, you have the Hall terms at the ion inertial lengths, and then you have the electron terms at the electron inertial lengths. And so for ideal MHD to be valid, all these terms have to be small compared to this V cross B terms. And so this gives us some limits on when ideal MHD is valid. And you can see that the Hall term, for example, is possibly these two terms, so the Hall terms and the resistance, become important before this electron inertia term does.